Welcome to our second lecture on research plumbing. If this were a trilogy rather than just a two-lecture series, there would be so many other topics I'd want to cover, among them row-wise operations, programming with dplyr, plot functions with ggplot, factors with forcat, strings with stringer, and dates with lubridate. But unfortunately, we don't have time for that this term. If you find yourself in a situation where you need to work with dates or strings or factors or any of these other items, however, I'd strongly recommend taking a look at some of these links. There are some really fantastic packages to make your life a lot easier. Much of the time that we spend when we're working on empirical research projects actually involves the nitty gritty of data cleaning and lots of little frustrating, irritating tasks. So, time that you spend investing in getting better at these tasks now is going to pay huge dividends over the course of your career. So, now that I've told you what I'm not going to talk about, let's dive into what I am going to talk about. I would be remiss if I did not show you how to merge data in a course on empirical research methods. And fortunately, there are some really helpful functions in dplyr for doing just that. These functions are called joins. So, a very common task in applied research is merging or joining multiple data sets. Let's say I've got a gradebook that contains student ID, name, and grades on various assignments. And then suppose I've got another file, emails, that contains student ID and email addresses. Well, I might want to merge these together into a single data set using this common student ID variable. So to do this, I'm going to use what is called a mutating join, which is some functionality from dplyr. And you can click on the link on the slide to read some more. But I will now introduce you to some of the basics. I've made up a fake gradebook for some fake students: Alice, Bob, Charlotte, Dante, Ethelberga, and Felix. You don't have to worry about any of the code on this slide. I'm just setting up some fake student ID numbers, some fake grades on some fake assignments: a quiz, 1, 2, 3, two midterms, and a final. All right, so now we've got this nice gradebook tibble, and let's try to merge it with another tibble. So here is my file of email addresses. So I've got email addresses for a number of students here. I have student ID and I have email address. And something I'd like you to notice is that not all of the people in this email list match with the students in my gradebook and vice versa. So when we try to merge, we might run into some issues. We'll have to think very carefully about what we would like to produce, given that the two files don't contain exactly the same people. In other words, what is our desired output? Because that's going to affect how we should carry out the merge. And there's no right answer. It really depends on what you're after. Okay, so as I mentioned, dplyr has something called mutating joins, and these are many different ways of trying to merge two data sets together that have a kind of common structure, but which one to use depends on what you want to achieve. So all of these join functions have two required arguments. X and Y are the tibbles that we want to merge. So we're going to start off with a left join, and you're actually going to learn about the other joins as an exercise, because we're reaching the point in the course now where I hope you're starting to feel a little more comfortable consulting the documentation for different packages and the help files. So I think it's very valuable to kind of get used to getting help on the fly. So I'll give you some examples and I'll give you some hints that will help you to figure out more on your own. I will begin by telling you what a left join is. So left underscore join x comma y returns a tibble with the same number of rows as x. So that's what the left in left join means. It refers to the leftmost tibble in the pair of tibbles x comma y. Let's see how that works with our gradebook and email tibbles. All right, so what I'm going to do here is I'm going to left join gradebook comma emails. And what did I get? Well, as promised, I got a tibble with exactly the same number of rows as gradebook, namely 6. And what students are in this data set? What students are in my gradebook? Well, as you can see, we have retained all the students whose ID appears in gradebook, but not in email. Who are those students? Well, we can see from the email column, where we have 3 NAs, that those students are Charlotte, Dante, and Felix. But we will be dropping any students whose ID appears in emails but not in gradebook. I'm going to repeat that because it's really crucial for understanding how a left join works. We're making sure that the result of this join includes all of the students who appeared in the leftmost tibble, in other words, in gradebook. But we're not necessarily going to include all the students who appeared in emails. We're only going to include them if we find a match for that student in our gradebook tibble. So what's happening here is that both of these two tibbles, gradebook and emails, have a common column, student ID. And what left join is doing is it's using that column to match up the records. When it can't find an email address for a student that's in gradebook, the unknown email address becomes an NA. All right, so now it's your turn to take a few minutes to try out an exercise. So you'll need to take a look at the dplyr help files. You can click on the links that I posted on the previous slides. So first, what I'd like you to do is copy, paste, and run the code that I used to generate gradebook and emails from the previous slides. You can always click on the little, if you move your mouse over the right-hand corner of one of my R code chunks, there's a little button that allows you to copy to the clipboard. So then I would like you to experiment. So you can try running a right join, guess what will happen, then see what happens, and then try to explain. Do the same for a full join and an inner join. Then I'd like you to think about how you might be able to rewrite my left join by using a pipe. Finally, I'd like you to add another column to the emails tibble. You can do this just using dplyr. And I'd like this column to contain the following names in order. Then I'd like you to left join to merge gradebook with emails. What happens? Now try setting the parameter by equal to, quote, student ID and see what changes. There's really nothing hugely complex going on here. You just need to experiment a little bit with how these joins work, and you will get the hang of it very quickly. So take a moment to pause the video, try out these examples, and as usual, you can consult the solutions on the course website. Once we know how to merge data, we're well on our way to becoming data ninjas. But the true dark magic of working with raw data, of course, is reshaping. And reshaping is perhaps for many people their most terrifying task because it seems like there are so many different ways for it to go wrong. But as usual, we've got some lovely functions from the tidyverse to help make our life easier. So in particular, we're going to be using the commands pivot longer and pivot wider from tidyr, which is part of the tidyverse, so you have already installed it. What's the point here? Well, sometimes you need to reshape data before you can plot or analyze it. You may have heard of the descriptors wide form and long form data. So we have these commands pivot longer and pivot wider that will allow us to move data back and forth from these formats. If you'd like some more details, there's a great article I've linked on the slides that provides some more information on pivoting. So how does this work? Well, pivot longer is where we'll start. Suppose that we wanted to use my silly little gradebook example to make a time series plot of quiz scores for each of the students in our class. Now, to make a plot like that, we'll need the data set to be arranged kind of like a panel, so a sequence of observations for the same individual made up over time. But notice that that's not actually how gradebook is set up. So gradebook actually has multiple observations over time in different columns, and we'd actually like those multiple observations to be in different rows and the same column. So what we're going to need to do here is increase the number of rows so that each student appears multiple times, once for each quiz. This may sound confusing, but it will become clear when you see exactly what we're going to do. So I'm going to show you the command here, and you'll see that the output is a bit longer. It doesn't quite fit on the slide, so I have to scroll. I'll start with gradebook. I am going to pipe it into the command pivot longer. I'm going to pass in some arguments, and I'll explain what those arguments do. So I have starts with quiz. All right, remember that one from when we were learning about dplyr. That's going to select all the columns that start with the word quiz. We had 3 of those: quiz 1, quiz 2, quiz 3. The next argument I'm specifying here is names underscore 2. So I'm setting names underscore 2 to quiz. And finally, I'm setting values underscore 2 to score. Finally, I am selecting student ID, name, quiz, and score. So let's see what's happened. Now, rather than a tibble with 6 rows, we have a tibble with 18 rows. So we've taken the 3 quizzes and we have put them on top of each other, so that now Alice appears 3 times, Bob appears 3 times, and so on. So there's a single column quiz that indicates which quiz we're referring to. So the first row has Alice, and it's giving her quiz 1 score. The second is going to give her quiz 2 score. The third is going to give her quiz 3 score. And those scores are stored in this additional column called, somewhat unsurprisingly, score. So you can see that what values 2 has done is it has told R where to put the values that used to be in the columns quiz 1, quiz 2, quiz 3. And you can see that the argument names2 has told R where to store the column names from which it got those scores. It's telling it to store them in a column that will be called quiz. So we have constructed 2 columns, quiz and score, and these 2 columns are providing the same information as we used to have in 3 columns. Those columns were quiz 1, quiz 2, and quiz 3. And what we've done here is we've basically set up a kind of a panel data structure. So if you want to think about quiz as like a time indicator, T is 1, 2, 3, and then score is just some outcome, like Y, that's precisely what we've done here. So if you remember from your panel data work that we stack observations for the same unit over time in exactly this way. So that's what pivot longer does. It makes the data frame or tibble longer by moving information that used to be stored across columns into a single column. So now let's just talk in a little bit more detail about what's going on. The arguments to pivot longer are data. That's going to be the tibble that we're going to pivot, and here I supplied that with the pipe. Cols chooses which columns to pivot, and I used a tidy select command because that makes my life much easier. Names2, again, tells us how to handle the column names from the cols that we've specified. And values2 is the column name in which we're going to store values from cols. So again, because this is a little bit complicated, I'm just going to repeat. We're starting with 3 separate columns, quiz 1, quiz 2, and quiz 3. And we're going to end up with 2 columns, quiz and score, but 3 times as many rows. Again, the column names from cols are like the time periods in a panel dataset. Now I'm going to show you that we can be a little bit fancier here, if we like, and we can kind of process the column names from the initial wider dataset when we extract them and put them into our nice long panel style dataset. So we can use the additional argument names underscore prefix. What that will do is that will actually strip off a prefix from the column, I should say a prefix from the column names that we're pulling. So here we pulled the columns quiz 1, quiz 2, quiz 3. We did that by using starts with quiz. What names prefix does is it says, hey R, listen, these columns you're about to pull out are all starting with a common identifier. That identifier is quiz. I don't need to keep that sequence of letters because it's the same for all of them. So cut that off and just keep everything that comes after that. And if you think back to the columns that we've pulled out, that's just going to give us 1, 2, 3. So this is a little bit tidier in the sense that now our column quiz, it gives the same information as before, but it just does it in a kind of a simpler way. So now the quiz is just an indicator of the sort of time period, if you will, in which the quiz took place. 1, 2, 3. I should be careful to point out that that's being stored as character data. So you can see that because of the little angle brackets CHR, but it's a bit tidier and nicer to read. Everything else in this particular example is completely unchanged. Now, you may not like the idea that we're storing those numbers, 1, 2, 3, as character. I sure don't. So if you want to make your way all the way to a bona fide panel data set with kind of like a time variable that is really numeric, we can do that for you. We can add an additional argument to pivot longer, and that argument is called names transform. Names transform needs to be given a list, and that list is going to specify what to do to each of the columns that we're processing. So here we're going to process only a single column. We're going to process the column quiz, which, remember, that's the new column that we create by pulling out the quiz scores from the original columns quiz 1, quiz 2, and quiz 3 and stacking them on top of each other. We create this column quiz that tells us which row corresponds to which quiz. So my names underscore transform is equal to list quiz equals as numeric. So what R will do here, it will apply the function as numeric to that column quiz. The output is exactly the same as before with one subtle difference. Now the column quiz is no longer character data. Instead, it's numeric. We can see the angle brackets DBL, which stands for double. Finally, we are ready to make our plot. So I am reproducing the entire pivoting pipeline from before, just for completeness, so you can see what happens. So we take our gradebook, we pivot longer, using all the fun tricks that we've just learned, including names prefix and names transform. Then we select the data that we need in line 7, namely student ID, name, quiz, and score. Finally, we pipe that into ggplot. So we're going to have our aesthetic mapping with X is quiz and Y is score. So quiz here works like the time variable, and Y is like the outcome. We will add some of our favorite geoms, geom line and geom point. And then, I don't know if you recall this from one of our early lectures about ggplot, but we learned how to use facet wrap to make a sequence of small plots that are faceted by a particular variable. That means that we have one for each value of that variable. So we're splitting the plots by name. That means we're going to end up with a different plot for each student. Finally, because I'm a bit of a minimalist, I'm going to use theme minimal. And here it is. It's not that exciting, but it's a time series plot for each student showing their quiz performance over time. Quiz 1, quiz 2, and quiz 3. There are other ways that you could have tried to make a plot like this, but this is probably the easiest. So when you're thinking about making a plot, you're thinking about doing some other kind of operation, the first question you might ask yourself is, if I could get my data into a slightly different format, would that make my life easier? If so, and the answer is often yes, then pivoting might come to the rescue and provide a nice, clean, and relatively simple way to get from what you want to an end result. Well, I guess I said that backwards. To get from where you started to what you want. If there is pivot longer, then surely there must be an inverse. There is. It's called pivot wider. So quite literally, these two functions are inverses. You can use one to undo the operations of the other. So if you start with a wide data set where many different columns store values for the same unit of observation, say over time, then we just saw that you can convert that to a long form data set by using pivot longer. Similarly, if you started off with a data set in long form and you want to get to one that is in wide form, you can use pivot wider. So pivot longer creates a tibble with more rows than you started with, and pivot wider creates a tibble with fewer rows and more columns. So to get started and to see how these two functions really are inverses of each other, let's store and display the results that we've already put together from above. There's nothing new here. It's just exactly the same code that we've already used. All right, so here is our tibble. It's running off the screen, unfortunately, so I'll scroll to show you that there are 18 rows, 3 for each student. All right. Now, suppose we wanted to go back to where we started. I know that's very silly, but this is just an example. So suppose that we wanted to return to the original wide form data set. How could we do that? Well, we'll use pivot wider. Now, the arguments that we need to specify for pivot wider are names from, names prefix, and names. Well, we don't have to specify names prefix. Well, we have to specify names from and values from. We can specify names prefix. So let's talk about how these different arguments work. Names from and values from work in exactly the opposite way in pivot wider as they did compared to pivot longer. So in this instance, names from says, hey R, where can I find the names that I'm going to use to construct my columns? Because remember, we're going to be going from this long form data set, which has a column quiz, 1, 2, 3, to this wide form data set. So we need to know where to get the names for the column headings here. And the answer is we're going to get the names from this column quiz in the long form data set. Okay, then where are we going to get the values from to construct these columns? Well, we're going to get them from the column score in the long form data set. Finally, names prefix, remember that that's something that is removed by pivot longer. Well, it's something that is added by pivot wider. And this all makes sense because what we're doing is we're reversing the transformation that we did before. So with pivot longer, we removed these prefixes. Now we're putting them back. Again, the best way to get used to this is just to try out some simple examples. So here I have an extraneous footnote, first of all, that you can ignore because this is a video, not an in-class exercise. But second of all, I have an exercise for you. So I'd like you to play around a bit with pivoting. And in particular, I'd like you to try out the Billboard dataset from Tidier. And I'd also like you to test out some examples that we've looked at before with KidScore from our kids dataset, and play around a bit with the gradebook as well. These exercises aren't too complicated, but they're very helpful, I think, for understanding how pivoting works. It takes a bit of effort to get your head around it, but once you see how it works, I'm sure that you'll find many examples in your own work where you can use this successfully. So why don't you take a few minutes to pause the video, try out these exercises, and as usual, you can find the solutions on the course website. Today is definitely a bit of a grab bag, so our final topic has nothing to do with our first two topics, and this is going to be a lightning introduction to parallel computing. We're going to use the FIR package, which, as you might have guessed, has something to do with the PER package. First, I would like to introduce the notion of an embarrassingly parallel problem. What does it mean to say that we're carrying out an algorithm in serial? Well, that means that we're going to pour milk on it and eat it with a spoon. No, it means that we're going to do it one step at a time. Parallel, on the other hand, means that we're going to do many steps at once. The CPU in your laptop almost certainly has multiple cores. These are effectively smaller processors within the CPU. If it does, then your CPU can actually execute multiple instructions at the same time. In other words, in parallel by spreading the work across these cores. We call a computing problem embarrassingly parallel, and if you want to read some more, you can click on the link here, if it's really easy to convert from serial to parallel. I know that's not a very satisfying technical definition, but that's the whole idea. Typically, that will mean that there are many independent tasks and that there's little or no need to exchange information between these tasks. A leading example, and one that's particularly relevant for this course, is Monte Carlo simulation. The thing about embarrassingly parallel problems is they're great. So don't be embarrassed to hunt for them. Basically, they're a free opportunity or nearly free opportunity to get just as much work done in much less time. just by leveraging the computational power that your computer already has at its disposal. So, there are several common approaches to parallelization of a Monte Carlo simulation, and here they are. First, we could hold the parameters fixed. So we could take the simulation parameters and then spread the simulation replications across cores. We could then repeat for different values of the simulation parameters. So here, again, we're spreading the simulation replications across cores. So if you think about replicating your simulation, I don't know, 5,000 times, if you had 5 cores, you could give each of them 1,000 of those replications. Then you could move to a new point in your parameter space and do the same thing. 5,000 replications, divide them across the 5 cores, giving each core 1,000 replications. And the key here is that each of those replications really can be executed completely separately from the others. There's no need for communication, and there's no need to really send a lot of data back and forth. That's the first option. Another option is to actually spread the parameter grid across cores. So in this case, what we would do is we'd have each core run all replications for that particular parameter configuration. So let's suppose we were running a simulation, and in the simulation, we had a parameter mu that could take on the values 1, 2, 3, 4, or 5, and we have 5 cores. Well, then we could take mu is 1, send that to core number 1, and that core will do all 5,000 replications. At the same time as we're doing that, we could send the value mu2 to core number 2. That core is going to do all 5,000 replications with mu2, and so on for the other the other 3 cores. So either of these approaches can work well, but there are sort of different scenarios in which you might prefer one relative to the other. So to get a meaningful speed up from the first approach, you really need to be in a setting where each simulation replication is relatively slow. And there's no hard and fast rule for what it means to say that each simulation replication is slow, but it's sort of all relative. On the other hand, we can always get gains from 2 in the following sense. That we could always just use a finer parameter grid. So if your simulation, takes a minute to run on 1 core, well, you could have 5 cores, look at 5 different points in the parameter grid, or even if it takes a few seconds to run, you could have each core looking at, 20 or 30 points in the parameter space, and spread across 5 cores, you could do hundreds of points. So there are many ways to divide the work, and you may have to think a little bit about how you want to do it in any given application, because the key here is something called Amdahl's law. So doubling of cores generally does not have the runtime. And there's a crucial reason for this, and one is that only part of your code is parallel. So the only thing that you can divide across the cores, the only thing that you can get a time savings on by parallelization, of course, is the part of your code that really runs in parallel. So if some of the code runs in serial, you can't get a speed up from that part. And that's one reason why doubling the cores won't necessarily have the runtime. But even more crucially, there's something called load balancing. If one core has less work to do than the others, it will finish early. So if you think about it, you really want to make sure that the cores are doing similar amounts of work. That can be tricky in practice because sometimes you don't know how hard a simulation is going to be at a given set of parameter values. It might be slower. There are certain problems that I've encountered where that happens, and you can't necessarily predict it in advance, so you may have to experiment a little bit. But the key point here is there is some kind of fixed cost, overhead, some kind of hardware and software limitations that can come into play that mean that actually there is some cost to parallelizing. It's not a free lunch. So the ideal situation when you're going to for parallelization is when you're going to be able to divide those fixed costs over many, many units and really over many periods of time. So let's say you have a simulation where every single point on the simulation grid takes an hour. That is a wonderful scenario in which to parallelize because you are going to get almost a halving of the runtime by running instead of on 1 core for 2 parameter values, running on 2 cores because the overhead is tiny. And let's suppose that the other parts of your simulation involve compiling results and other simple operations like that. Then the part of your code that's not parallel is really small in runtime relative to the part of the code that is parallel. So the gains that you're going to get from parallelization depend on all these other factors. It takes some experimentation, but Monte Carlo simulation is an excellent opportunity to reap the benefits of the cores that your computer has inside. Fortunately, this is really easy. You don't have to learn any complicated low level programming. You can just use a package called FIR. So there's another package called Future, and Future provides asynchronous evaluation of our expressions. There are three different variants of this. First of all, there's multi-session, which creates background R sessions on your current machine. Second of all, there's multi-core, which creates what are called forked R processes on the current machine. That only works on Linux and Mac. And then there's cluster, which creates external R sessions on a current, local, or remote machines. So FIR uses Future to run per commands in parallel. And from your perspective, you don't need to know anything about Future. You don't need to know anything about multi-session, multi-core, or cluster. All you need to know is that you prefix your favorite per functions with future underscore. For example, future underscore map and future underscore pmap are parallelized versions of map and pmap from per. So let me show you now the simplest possible example of FIR. I'm going to load this FIR package, which if you haven't installed it yet, you'll need to do. I'm also going to load another package called TikTok, which is not a social media platform, but is an easy way to time code chunks. Now I'm going to create a really exciting function. My function is called wait 2 seconds. What it does is it waits 2 seconds by using the command sys.sleep2. That's in line 4. And then it prints out done waiting. All right, I'm now going to run this code in serial. So I'm going to use map character in particular, to repeat this function 4 times. So if all is right with the world, running a function 4 times that does nothing except wait for 2 seconds and then print some output should take about 8 seconds. And indeed it does. So with my tick and my talk, I get about 8.012 seconds elapsed. All right, now if you thought that was dumb, wait until I parallelize it. So here's all that you need to do to use future map. So first, we have to set up the parallel processing setting. So we use this command in line 2, plan multi-session workers equals 4. So what I'm doing there is I am telling R that it needs to plan to run in parallel, and it's going to run in parallel on 4 cores. So setting the number of workers is basically setting the number of cores on which the parallel processing is going to run. So I am now going to time this, and using TikTok again, I'll do exactly the same thing. I will run wait 2 seconds, but now I'm running it in parallel. So each of the cores is going to be waiting 2 seconds at the same time. Let's see what happens. Well, it took 2.869 seconds. Not bad. It's a big speed up over the original 8 seconds. But as you can see, we didn't actually divide the runtime by 4, because as I mentioned before, there are other things going on that create costs, in particular setting up the parallel processing, dividing the jobs among the various cores, and collecting the output. But nevertheless, we have done our very first example of parallel programming, and it more or less works as expected. But probably you'd like to use parallel programming for something more exciting than just waiting for 2 seconds. So let's recall the MLE bias simulation that we wrote in an earlier lecture. Here I'm just reminding you of the code that we used. We wrote a function to draw some random normal variates with a particular standard deviation. Then we had a function to create estimates for the population variance. So the usual estimator, namely the sample variance, and the MLE, which divides by n rather than n minus 1. Then we wrote a function to run the simulation at specified parameter values using some of our favorite per functions. So now we have run sim, which runs the simulation study for specified values of n, the sample size, and s squared, the population variance. Now, just to remind you how we did this last time, we ran the simulation over a grid of parameter values. In particular, as you can see in line 2, simparams gets expand grid, n equals 3 to 5, s squared equals 1 to 3, that sets up a grid of 9 parameter values, all the combinations of 3 to 5 and 1 to 3. The line number 3 in this code block runs the simulation over all of those points in the grid using pmap. And then beneath, we show how we summarize the results, and we created a nice table of summary statistics. So you can see that there were, again, 9 grid points, and we summarized the information for each of them. Okay, so all that we're going to do is we're going to take that line 3 that says sim results gets pmap sim params run sim, and we're going to replace that with future pmap. So again, the simulation for each point in our parameter grid and sigma squared is independent of all the others, and all we need to do to run them in parallel is use future pmap. Now there is one complication here, and that involves setting the seed. So it turns out that the Mersenne twister, which is our favorite RNG we learned about in our lecture on Monte Carlo simulation, only runs in serial. But parallel simulations require parallel pseudo RNG. Such things do exist, but they use different algorithms. You can still set the seed, but you have to note that serial and parallel are not going to agree with each other. So if you set the seed and you run in parallel, you can reproduce the results when you run in parallel again. But if you set the seed in serial, it will not match what you get when you run in parallel. I've added a link on the slide if you'd like to read some more about that. All right, so let's set this up. We're going to do a timing comparison of running in serial, as we did in our original lecture on simulation, versus running on 4 workers. So just as before, I'm setting up sim params using expand grid, and I'm running sim results gets pmap sim params run sim. So you can see that when I run this particular simulation study in serial, on my machine at least, it takes about 12 seconds. Now I'm going to make a slight change. So first of all, I'm going to plan for a multi-session computing environment. So I'll set plan multi-session workers equals 4. Now I will set the seed, and I'm going to specify my options fur underscore options seed equals true. So I'm going to need to pass this in when I use future pmap to make sure that I am setting the seed correctly. Then I'm going to time this command in line 5, sim results gets future pmap. Everything else is exactly the same as above, except now I'm specifying these options with the dot options argument. So compared to the top code block, I've really only added 2 additional lines of code. So I've just added that plan multi-session, and then I've specified some options just for setting the seed, but there was no new programming required. So this is basically for free. Now, with 4 workers, we did not divide the runtime by 4 because we started with 12 seconds and we ended up with 5 seconds, but that's still a pretty serious speed up. And if my initial simulation took not 12 seconds, but 12 hours, I'd be pretty happy to cut it down to 5. So I would strongly encourage you to think about ways that you might be able to use parallel computing in your work, because with FUR, it's almost for free. So now you can see why I sort of insisted on us using the PUR package to begin with and thinking about functional programming. It's because it allows us to really abstract from low-level concepts like a for loop, and instead to think about general concepts like map, which will allow us to use really powerful packages that can understand the structure of our computation and then can sort of initialize the right kind of parallel processing that makes sense given what we mean to do. So there's a lot of value in abstraction, and that's one of the nice things about this functional approach to programming. All right, well, if I haven't convinced you yet, maybe this exercise will do the trick. So this is pretty similar to the example that I just showed you, which involves looking at the bias of the maximum likelihood estimator of the population variance. So basically, all I'm asking you here, and you have infinity minutes to spend on this, by the way, not that it should take you quite that long, is to try out the same idea for covariance. So we have the sample covariance, which divides by n minus 1, and then the MLE, which actually divides by n rather than n minus 1. So you can sort of follow along with the functions I've already written make some minor modifications, and then you can try to carry this simulation out over a grid of parameters and see how running it in parallel changes the runtime.